Imagine this. 3 tiny glass spheres, each smaller than a grain of dust, suspended in midair. No strings, no magnets, no tricks, just floating. Now zoom in closer. These spheres aren't just hanging there, they're trembling, vibrating with a rhythm so faint that no ordinary instrument could ever hear it. But that trembling isn't random, it's the pulse of quantum energy at work. A group of physicists at ETH Zurich has done something extraordinary. They've levitated a cluster of glass spheres so perfectly balanced that nearly all of its movements are ruled not by classical physics, but by quantum mechanics. And this strange, shimmering object? It could open the door to technologies we've only dreamed about: navigation without GPS, medical scanners that can see the unseen, even sensors that could one day detect the elusive particles of dark matter itself. Let's step into their lab for a moment. The room is dim. A thin beam of golden light cuts through the air. At its center, 3 spheres, stacked like a tiny tower of marbles. They hover silently, glowing softly in the beam. Each one is a few hundred nanometers wide, about 1/10 the thickness of a human hair. But to hold them steady requires unimaginable precision. A single air molecule, a tiny vibration from outside, even a whisper of heat, could send the whole thing tumbling. And yet, somehow, Professor Martin Frimmer and his team managed it. They held this fragile structure perfectly still, counteracting gravity itself, at room temperature. They call it a levitating nano cluster. To them, it's not just an experiment, it's a controlled conversation with the quantum world. And what they found inside that conversation changed everything. If you look closely, the cluster isn't frozen. It's shivering, a delicate wobble, like a compass needle searching for north. That tiny motion isn't noise or error. It's something far stranger. Because according to quantum mechanics, nothing in the universe can ever be completely still. Even in total darkness, even in the deepest vacuum, every atom, every particle, is always jittering, always alive with invisible motion. Physicists call this the zero-point fluctuation. It's the restless heartbeat of the quantum world. Lorenzo Dania, a postdoc in Frimmer's lab, puts it simply. The larger an object is, the smaller these quantum fluctuations become, and the harder they are to see. But ETH Zurich saw them. They detected the tiniest quantum shiver, in an object made not of a few atoms, but of hundreds of millions. The cluster quivered 1,000,000 times per second, each movement only a few thousandths of a degree. And 92% of that motion came purely from quantum mechanics. That number, 92%, might sound abstract, but it's a record-breaking level of quantum control. Almost total quantum purity, achieved with something big enough to see. Here's the twist that shocked even the researchers. Most experiments like this need extreme cold, temperatures just above absolute zero, to prevent heat from ruining the delicate quantum motion. But this was done at room temperature. No cryogenic cooling, no liquid helium, just air-conditioned lab space and an absurd level of control. In their measurements, 92% of the cluster's movement came from quantum effects, and only 8% from classical noise. Frimmer compared it to inventing a new kind of truck, one that carries more cargo than ever before and somehow uses less fuel. In the world of quantum physics, that's like building a bridge between 2 universes, the everyday world we see and the hidden quantum world beneath it. So, how do you suspend glass in midair using nothing but light? The answer lies in something called optical tweezers, a technology that uses the pressure of laser light to trap and hold microscopic objects. Here's how it works. Inside a vacuum chamber, the team focuses a powerful laser through a lens. The light's electric field exerts a tiny force on the glass particles, pulling them toward the brightest part of the beam. There they hover, balanced between gravity and the pressure of light itself. Now imagine not 1, but 3 of these spheres, stacked in a vertical line, each one perfectly aligned, held steady by invisible fingers of photons. That's what the ETH team built. A nano tower, so sensitive that a single stray photon could knock it off balance. Yet, with careful feedback control and exquisite tuning, they kept it steady. No wires, No supports, just light and patience. It's a small miracle of precision and a stepping stone towards something much bigger. Once you can isolate a system so cleanly that 92% of its behavior is quantum, something magical happens. You can start using it as a sensor for the universe's faintest forces. For example, dark matter, the invisible mass that makes up 85% of the cosmos, yet has never been directly detected. If a particle of dark matter were to nudge this levitating cluster, even slightly, it might produce a measurable shift in the cluster's vibration. In other words, these floating glass spheres could become a dark matter detector. But that's not the only promise. Such ultra-sensitive sensors could measure gravitational effects at microscales, helping physicists probe how gravity and quantum mechanics, two of nature's most powerful forces, interact. And beyond physics? The same technology could revolutionize medical imaging, detecting biological signals so faint that current machines can't even register them. Or imagine GPS-free navigation systems, where a quantum motion sensor tracks your position precisely anywhere on Earth, no satellite required. That's what happens when quantum control leaves the lab and enters the real world. Of course, this is just the beginning. The setup is still large and delicate, but the principles are clear and scalable. For the first time, researchers have a room-temperature quantum system, stable, affordable, and almost perfectly isolated from the outside world. Frimmer's team now has a launch pad for everything that comes next. Sensors, computers, experiments exploring the very fabric of space and time. He put it best. We now have a system that's relatively simple, cost-effective, and perfectly suited for exploring quantum phenomena. In science, that's code for the real story starts here. So maybe, somewhere in a quiet Zurich lab, surrounded by lasers and silence, we're watching the birth of something extraordinary. 3 glass spheres, floating in nothing, whispering to the quantum world. Their tiny shiver, a message from the edge of what we know. Today, they're just hovering specks of glass. Tomorrow, they might help us see the invisible, dark matter, hidden forces, the true heartbeat of reality itself. Because sometimes, the biggest revolutions begin with the smallest tremors.